So in the last video, we have calculated the moment of inertia of a rotating molecule. Now let us see the expression for rotational energy level. Rotational energy. Expression for rotational energy. So in this expression for rotational energy, by solving the Schrodinger wave equation, we get Ej is equal to h over 8 pi square I j into j plus 1. So this is obtained by solving the Schrodinger wave equation. Ej is equal to h over 8 pi square I j into j plus 1, where j is the rotational quantum number, I is the moment of inertia we have calculated in the last video. Ej is the expression for rotational energy in the infrared spectroscopy. Now we can find out that when there is excitation from j is equal to 0 to j is equal to 1. So therefore the molecule, it absorbs energy from rotational energy level j is equal to 0 to j is equal to 1. Now it emits the absorbed energy, it comes back from the energy level, rotational energy level, j is equal to 1 to j is equal to 0. Therefore we can write Ej is equal to h over 8 pi square I j is 1 into 1 plus 1 minus h over h squared by 8 pi square I j into j plus 1. J is equal to 0 plus 1. Now 1 into 1 plus 1 is 2. Therefore this becomes, the whole thing becomes 0. Therefore Ej is equal to h squared by 8 pi square I. This 1 plus 1 into 1 is 2. And this Ej is nothing but the energy emitted when it jumps from j is equal to 1 to j is equal to 0. That is delta E. Delta E is equal to h nu, where nu is the frequency of the radiation, h is the Planck's constant. Now you substitute this, and we can also write this c is equal to nu lambda, or nu is equal to c by lambda, or this is equal to c into nu bar. So in the place of delta E, you can substitute delta E is equal to h c nu bar. Now delta E, you substitute here, h c nu bar is equal to h squared by 8 pi squared I into 2. Here nu bar is equal to h squared by 8 pi square I c into h into 2. Now you cancel h, it will be cancelled. Similarly 2 into 4 times. So therefore nu bar is equal to h over 4 pi squared I into c. Therefore this is the wave number nu bar. It can be experimentally determined. Nu bar is equal to h over 8 pi square IC, and we know that I is equal to moment of inertia. I is equal to mu r naught square. I is equal to mu r naught square. Now you substitute this I is equal to mu r naught square here. In this expression we get nu bar is equal to h over 8 pi square mu r naught square into c. So we have substituted in the place of I is equal to mu r naught square. We have substituted here. Now where r naught is the bond length and this nu bar is the wave number. It can be obtained from the spectra. and this mu reduced mass can be calculated for a particular molecule. This R naught is the bond length. So R naught bond length can be calculated. Now R naught square is equal to nu bar comes to the denominator, h by h over 8 pi square mu c into nu bar where nu bar is experimentally determined. Mu is the reduced mass of the molecule. Therefore, R naught bond length can be calculated by the expression R is equal to square root of h over 8 pi squared mu c into nu bar. So this is the expression for rotational energy. By this expression, we can find out the bond length R naught between a diatomic molecule, and by knowing its reduced mass, wave number from the experiment, we can find out the bond length. Bond length can be calculated. That is the advantage. Bond length of the molecule can be calculated like this. So similarly, we can find out the rotational constant. Rotational constant for this molecule. Rotational constant is the characteristic of particular infrared spectra. That is also. So first thing is determination of bond length. So by this rotational energy expression, Ej is equal to h square by 8 pi square j into j plus 1, we can find out the bond length of the molecule R naught by the expression R naught is equal to h by 8 pi square mu c into nu bar. Similarly, we can find out another important term here, that is called rotational constant. Rotational constant is the characteristic of IR spectra, rotation, infrared spectra of this rotational energy, this particular molecule. So we know that Ej is equal to h square by 8 pi square I j into j plus 1. Suppose if it goes from j is equal to 0 to j is equal to 1, it emits the energy and it comes back from j is equal to 1 to j is equal to 0. Now let us find out the value of rotational constant. Rotational constant expression can be obtained like this. Ej is equal to E2 minus E1, that is delta E. Delta E is equal to h square over 8 pi square I j into j plus 1. Now this delta E is equal to h nu. H nu is equal to h squared over 8 pi square I, where nu is the frequency of infrared radiation. This frequency range, this frequency quantization, that quantum of this frequency can be determined here. We can write frequency nu is equal to h square over 8 pi square I into h cancels. So therefore nu is equal to h by 8 pi square I j into j plus 1. This constant h by 8 pi square I, it is a constant for a particular infrared infrared ray absorption or emission. H over 8 pi square I is a constant for a given molecule. That constant is represented by nu is equal to b j into j plus 1, where b is called the rotational constant. Rotational constant for a particular molecule, rotation constant, and it is characteristic of emission or absorption of radiation in the infrared region. Nu is equal to, that frequency of that radiation is equal to rotational constant into rotational quantum number. Suppose if it goes from j is equal to 1 to 2, suppose if it goes from j is equal to 1 to 2, from first position, let us say first you take j is equal to 0 to j is equal to 1, let us see the value. Now nu when it goes from j is equal to 1 to j is equal to 0, the value becomes b into 1 plus 1 minus b into 0 into 1 plus 0. This becomes 0. This becomes nu is equal to, or 1 plus 1 is 2, 2 into 1 is 2, this becomes 2b. See the rotational constant, the energy level, energy difference between one absorption quantum number to another absorption quantum number. Now, if the absorption is from j is equal to 0 to j is equal to 1, or emission from j is equal to 1 to j is equal to 0, it is equal to b, 2 times the rotational constant. That frequency is equal to 2 times the rotational constant. Suppose if it is goes from j is equal to 1 to j is equal to 2, what is the frequency value in terms of rotational constant? We know that nu is equal to b into b into j plus 1. Now j is 2 into 2 plus 1 minus b into 1 into 1 plus 1. So this becomes nu is equal to this 2 plus 1 is 3 into 2 is 6. This is 6b minus this is 2b. So 6b minus 2b, this becomes 4b. So first range, frequency range is 2b when it goes from 0 to 1. Second frequency range, when j is equal to 1 to 2, it becomes 4b. Now let us see the value of a frequency in terms of rotational constant when it goes from 2 to 1. When it goes from 2 to, not 2 to 1, 2 to 3. This is what, this is 0 to 1, this is 1 to 2, this is 2 to 3. When it goes from energy level, rotational energy level 2 to 3, frequency value becomes nu is equal to b into 3 plus 1 minus b into 2 plus 1. Now this is equal to 3 plus 1 is 4, 4 into 3, 12, 12b minus, this is 3 into 2 is 6, it becomes 6b. So 12b minus 6b is 6b. Now you see the rotational range. It is 2b, nu is equal to 2b, 4b, 6b, and so on. The difference is 2b. Therefore, the energy level we can represent like this. This is 0, this is 2b, this is 4b, 6b, and so on. The difference, the energy level in terms of rotational quantum number, it is always a constant, that is equal to 2b, 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 and 2b. So this is the advantage of calculation of rotation. What is that? Rotational quantum number, a rotational constant b. So rotational constant b is very helpful in knowing the energy difference. So in between, energy will not be absorbed or emitted. These energy levels are quantized. The values are fixed. Therefore, absorption or emission will be taken place only in this range, 0, 2b, 4b, 6b. The difference is only 2b between the any two in rotational energy levels. That is the advantage. So while writing, we have written nu bar is equal to h over 8 pi squared IC, but it is 4. You make it 4 place. Instead of 8, you make it 4 pi squared IC. So therefore R naught becomes, it is not h by 8 pi squared mu mu bar c. You make it 4. So it becomes root of 4 pi squared mu nu bar into c. So by knowing the frequency, by measuring the frequency of infrared spectra, we can find out the bond length R naught. Now in this absorption of rotational vibration, rotational energy, a specific range, a specific amount of energy is observed. Therefore, the rotational energy level is quantized, and the quantum, the rotational energy, quantum of energy is a specific rotational quantum number. Therefore, only excitation from j is equal to 0 to j is equal to 1 or 1 to 2, 2 to 3 like that, it is allowed. In between, excitation is forbidden. Therefore, the selection rule for rotational quantum number is delta j is equal to plus or minus 1, where delta j plus 1 indicates the absorption of energy in the rotational energy level, and delta j is equal to minus 1 indicates the emission of radiation. Therefore, the rotational quantum number, rotational level is quantized. In between, that absorption or emission is forbidden. That is about selection rule. Now, come to the isotopic effect. Now, in this rotational spectra, the rotation of the molecule depends upon the mass, depends upon the reduced mass mu. Therefore, rotational spectra, it depends on them. If there is isotopic elements in the molecule, what happens to the rotational quantum number J? So, if you see that the rotational quantum number, as the mass increases, as the mass of the isotopic atoms increases, the rotational level also decreases. This can be calculated by taking the frequency R naught is equal to h over 8 pi squared IC. We know this, where I is the moment of inertia. You substitute for moment of inertia I, it becomes mu is equal to h over 8 pi squared I is equal to mu r naught square c. Here the mu changes for the isotopic substitutions. Therefore, this rotational constant B is different for two different isotopic substances. For one isotope, for example, if you consider two isotopes, C12O16 and C13O16, the moment of inertia, if this is mu, if the moment of inertia of this becomes a mu bar. Therefore, rotational quantum number changes. If you take the ratio of rotational quantum number with one isotope divided by another isotope, B by B dash, that becomes mu1 by mu, this becomes h over 8 pi square mu r naught c square into 8 pi square mu r naught c square divided by h. Now h cancels, all the terms are cancelled here, because for b dash it becomes mu dash. So mu dash by mu is different for two substances, for two isotopes. All other are constant and they cancel with each other. Therefore, b by b dash is equal to mu dash by mu, because their reduced masses are different. So b by b dash, rotational constant b by b dash is equal to mu dash by mu. Therefore, by knowing the frequency, we can find out the reduced mass of the isotopic molecule. When the atom is substituted by an isotope, the rotational quantum level is decreased, and J values becomes less when compared to non-isotopic molecule. In case of isotopic molecule, the rotational energy level is decreased. By measuring the frequency of this decreased rotational energy, we can find out the mass of the isotope. Thus, the isotopic amount, the percentage of isotopic element present in a molecule can be calculated. can be calculated. That is the advantage of this rotational spectra. So isotopes can be measured and it can be determined by measuring the rotational constant of different isotopic substances. That is about selection isotopic effect in case of molecules. So now we have vibrational spectra. What is vibrational spectra? What are the importance of vibrational spectra? After studying this rotational spectra, let us pass on to vibrational spectra. Vibrational level has got high energy. So each vibrational level, it consists of a number of rotational level. So each vibrational level consists of a number of rotational level. Rotation quantum number V is equal to 0, V is equal to 1, V is equal to 2, etc. In between we have a number of rotational level. J is equal to 0, 1, 2, 3, etc. These are the J values. Now, by solving the wave equation according to wave mechanics, this energy EV between any two vibrational energy levels is given by the equation half plus V into Hc omega, where omega is called the oscillation frequency. This is the oscillation frequency of the vibrating molecule. So molecule for vibration, the energy level is a little bit more. So therefore here a near infrared radiation is observed for the vibration of the molecule. For vibration of the molecule, the energy is more. In between a number of rotational energy levels are there. So this vibrational energy level is more when compared to rotational energy level. So therefore, if suppose rotational energy is 0, there is no absorption in the near infrared region. What happens to this equation? EV becomes, if V is equal to 0, half into Hc omega, where omega is the frequency of oscillation, c is the velocity of light, h is Planck's constant. So it becomes, even though V is equal to 0, there is minimum energy. There is minimum vibration in the molecule, even though there is no absorption in the infrared region, near infrared region. This energy is called 0 point energy. 0 point energy. So the minimum amount of energy is there, even though there is no absorption of energy. And this minimum energy, 0 point energy, the molecule has got this minimum energy even at 0 Kelvin. Even though when the temperature reduces to 0 Kelvin, there is minimum energy. That minimum energy is due to the bonded electrons interaction among themselves. Therefore, this is called 0 point energy. 0 point energy is the minimum energy of vibration by the molecule. That energy will exist, energy will be there in the molecule even at absolute 0. This is called 0 point energy. So by solving this wave equation, we can find out the oscillation frequency omega is equal to 1 by 2 pi root of k by mu, where k is called the rotational constant. During rotation, there is a simple harmonic motion. So there is a displacement from the original level. So this is the original length between two atoms. So there is a vibration in the molecule. When the energy is absorbed, this vibration is increases and there is a stretching. The molecule, the bond stretching will be there. So this is a stretching, bond stretches. This is the equilibrium length of the bond. So there is a stretching in the molecule. So for this stretching, force is required. So the force which is proportional to the change in the length of the bond. That is delta x, delta this bond, delta x is the bond length which increases. That is directly proportional to the force of this vibration. That is due to absorption of infrared radiation. This force increases the length. So this displacement is directly proportional to the force. This force, you can write this equation as F is equal to K into delta x. So here because of the force, there is a increase in the length of the bond. Therefore we can represent it by minus sign. So minus sign. Now F is equal to minus K when delta x is equal to 0. This means that when the delta x is equal to 1, when the displacement is unity. Now this F is equal to minus K. This is called force constant. Force constant. Force constant. Now we can define this force constant as the force that is required to bring back to the original level. That is at the unit displacement. So this is the force constant K is defined as the force required to reinstate, to bring back the stretched molecule to the original position when the displacement is unity. Therefore, this constant is force constant. We can write K is equal to minus F, force required to bring back that. So this is called force constant. Here, this is force constant and force constant of vibration, and this is the reduced mass of the molecule. So now by wave mechanics, we found that oscillation frequency omega is equal to 1 over 2 pi into root K by mu. We can rearrange this. You take omega square it, you will get 1 over 4 pi square into K by mu. Now this omega can be converted into omega bar. Omega bar is equal to omega is equal to HC, or omega bar is equal to H into omega bar is equal to H into omega. So omega bar is equal to 1 over 4 pi squared, 1 over 4 omega 4 pi squared into C squared, HC. So omega is equal to H into C by omega, or omega bar is equal to the C by omega is equal to omega bar is equal to W square into C square. Now you substitute C square here. Omega bar squared is equal to 1 over 4 pi squared C squared into K by mu. Omega squared is the oscillation frequency number. So therefore omega square is equal to 4 pi squared C K by m. Therefore this K we can calculate here. K is equal to omega bar squared 4 pi squared C squared into mu. So this force constant can be calculated by measuring omega square, oscillation frequency. C is the velocity of light, mu is the reduced mass. So therefore, by knowing all these terms, we can find out the force constant of a molecule. This force constant of a molecule is characteristic of the molecule, and this can be determined, force constant. Now for this vibrational motion, for this vibrational absorption, this quantum number, this vibrational quantum number is also quantized. Therefore the excitation from V is equal to 0 to V is equal to 1 is possible. In between, the vibrational energy absorption is forbidden. Therefore, as in case of rotational quantum number J, this vibrational quantum number V is also is also vibrational quantum number is also has got value plus or minus 1 unit. So this is the selection rule for vibrational quantum number. V is equal to plus 1 means absorption of infrared radiation to excite from one vibrational level to another vibrational level. V is equal to 1. V is equal to minus 1 means emission of absorbed light when it comes from V is equal to higher level to the next lower level, it is minus 1. Plus 1 indicates absorption, minus 1 indicates emission of the radiation. Therefore, this is the selection rule for vibrational spectra. So, vibrational spectra is the selection rule. It absorbs only in the near infrared region, whereas for rotational absorption, rotational emission, it takes place in the far infrared region and microwave region. This is about vibrational spectroscopy. And when it absorbs higher energy, vibrational energy level, the molecule undergoes different vibrations, different modes of vibrations. So if you see the different modes of vibration, vibrational modes of polyatomic molecule, there is stretching and bending of molecules. There is stretching and bending of molecules. So in case of stretching, what happens? There is symmetrical stretching. The bonds is stretched in this way, symmetrical stretching. So symmetrical stretching of bonds takes place in some molecule. In some molecule, there is asymmetric stretching. Symmetrical stretching or asymmetric or unsymmetrical stretching. There are two types of stretching in the molecule, two types of vibrations. Stretching vibration. In stretching vibration, there is two types of stretching. Symmetrical stretching, this is symmetrical. Symmetrical stretching, this is unsymmetrical stretching. So, with respect to the bond, there is symmetrical stretching. The bond length in both the cases, it increases. Whereas in case of unsymmetrical stretching, if one bond is increased, another bond is decreased. So, this is stretching of the bonds, symmetrical stretching and unsymmetrical stretching. The absorption of energy is different for symmetrical stretching and unsymmetrical stretching. In case of bending vibrations, there are four types of bending vibrations: scissoring, rocking, twisting, and wagging. There are four types of bending vibrations. Bending about the bond. This is stretching about the bond. So this is with respect to two bonds. The bond may be the bond angle may be increased or decreased. Therefore, that is bending frequency. So, if both the atoms come inside, the bond angle is reduced. They come together, they come closer. That type of bending of the molecule is called scissoring. So, scissoring frequency is different from stretching frequency. Scissoring. So, we can find out the scissoring frequency in the molecule. So, in case of rocking, both the atoms, they go towards same side, not like opposite side, same side. If they go towards same side, that is called rocking. So both the molecules, they go towards the same side. That is rocking. In case of twisting, one molecule come above the plane, another one atom come above the plane, another atom go below the plane. One above the plane, another below the plane. So that type of vibration is called twisting vibration. Twisting, the molecule is like the twisting vibration is there here. Another type of vibration frequency is wagging. In case of wagging, both the bonds either they go upwards or downwards. Both the bonds. Therefore, that is wagging. So these scissoring, rocking, twisting, and wagging frequencies are different. By knowing these frequencies, we can have an idea about the structure of the molecule. So this is a different type of vibrational motions in the molecule. Therefore, these vibrations, they have got different energy levels. Therefore, they absorb the different energy levels here. So this is about different modes of vibration. So in case of vibrational spectroscopy, we can find out the structure of the molecule. But here, for the vibrational level, higher energy is required. That is in the near infrared region. For rotational spectra, it is in the far infrared region or microwave region. And by studying the isotopic effect, we can find out the bond nature, whether it is single bond, double bond, or triple bond. So bond nature can be predicted by studying the vibrational and rotational spectra. So the structure can be identified, the structure can be predicted by studying this infrared spectra, that is rotational spectra and vibrational spectra.